Chapter 5, Unit 6. We're going to begin looking ahead to inferential statistics. Inferential statistics use information from samples to answer questions about populations. They help interpret the results from research studies. So a typical research study begins with a question about how a treatment will affect the individuals in a population. If individuals in the sample are noticeably different from individuals in the original population, then the researcher has evidence that the treatment did have an effect. If the sample is not noticeably different from the original population, it would appear that the treatment has no effect. So here's a diagram of a research study. You start with an original population without a treatment, and you choose a sample from that population. You give the sample people the treatment, and then what you have is a treated sample. So we're going to talk about detecting noticeable differences. We're going to talk about detecting noticeable differences. We're going to use Z-scores to do this. And notice in the body, in the middle of the normal distribution here, 95% of the scores are all in the middle. And then in the two tails, anything greater than or less than 2 standard deviations away from the mean, those will be extreme scores. So Z-scores greater than plus or minus 2 indicate a noticeable difference from other scores in the distribution. These are extreme scores. They are in the tails. So here are the extreme scores. Z-scores less than plus or minus 2 are not different than the other scores in the distribution. They're called central scores. They're in there with the other 95% of the scores. They're highly representative of the population if they're in the central area. So in this chapter, boundaries of plus and minus 2 for Z-scores are not determined by probabilities. In future chapters, probabilities will be used to determine the boundary. So it may not be plus and minus 2. It might be plus and minus 1.96 or plus or minus 1.64. We'll talk about those later when we get into those chapters. So let's look at this example. Adult rats weigh an average of 400 grams. The distribution of weights of rats is normal with a standard deviation of 20 grams. The researcher selects one newborn rat and injects the rat with a growth hormone. When the rat reaches maturity, it is weighed to determine whether there is any evidence that the hormone has had an effect. Assume that hormone-injected rat weighs 418 grams. Is this noticeably different from the regular rats that did not receive any hormone injection? Part B, now let's assume that hormone-injected rat weighs 450 grams. Is there a difference now? So first off, you're going to draw your picture, and you're going to do your table at the bottom, mean of 400, standard deviation of 20, so fill in your lines. You go ahead and put the standard deviations or the Z-scores down there, 0, 1, 2, -1, and -2, okay? And I would go ahead and notice that anything beyond 2 for this problem is going to be extreme individual. So you notice they drew lines where the 2 is. And then they put the scores, they drew lines coming up from the bottom for x equals 418 for part A. And they drew a line where x equals 450 would be for part B. So if you're going to just draw your picture and look at this, you can easily see that if the rat weighs 418 grams as in part A, they're in there with the population of the other non-treated rats. They're in the central area with everyone else. And you're going to notice for part B that x equals 450 is definitely beyond that Z-score of 2. So it's extreme. So there was a difference there. That rat is completely different from the other ones. So there would be a difference for part B. So let's look at what happens when we calculate a Z-score. So if we look at the Z-score for part A, we plug in the numbers, we get 0.90. That confirms our suspicions. Our Z-score is right there in between the -2 and +2 standard deviations or Z-scores. So the result is that the hormone does not have an effect on weight. Now let's look at part B, calculate a Z-score here, and we get 2.5. Definitely beyond the Z-score of 2.0 in those what we call rejection regions in those tails there. And we say the hormone does have an effect on weight. So learning check problem 1, see if you can solve the problem, pause the video. For the last 20 years, the high temperature on April 15th has averaged 60 degrees with a standard deviation of 4. Last year, the high temperature was 75 degrees. Based on this information, last year's temperature on April 15th was a little above average, far above average, but impossible to describe how much, or there's not enough information. Well, I would say do a table. Really quick and easy. Where does 75 degrees fall? It falls way above the standard deviation of 2, which is the cutoff for extreme, so you know that it's far above average. You can confirm this by calculating a z-score. You would end up with a z-score equals 3.75, which is definitely, again, far above average. Anything above 2 would be really extreme, far above average. Learning check problem 2. Go ahead and pause the video, see if you can work the problem. A score of 75 is obtained from a population. Which set of population parameters would make x equals 75 an extreme unrepresentative score? So keep in mind that an extreme score would give you a z-score greater than 2 or less than negative 2. So if we found a z-score for part A, we would end up with 1.25. That's a central value. It's in there with all the other scores. Part B, we would find a z-score of 3.33, which is definitely an extreme unrepresentative score. It's in those tails way out there in the extreme regions. Part C, we'd find a z-score of 0.62, again right there in the middle between negative 2 and positive 2 standard deviations, so the z-score would be right in the middle, be a central score. Part D, z equals 1.67, again a central score. So our answer here would be B. That is, these population parameters would give x equals 75 as an extreme unrepresentative score. Learning check problem 3. Under what circumstances would the score that is 20 points above the mean be considered a more extreme score? So, part A says when the mean is much larger than 20. Well, let's look at an example and let's think about this first. So if you look at the equation z is equal to x minus the mean over the standard deviation, and then you also have to realize that a more extreme score means a higher z-score. So let's just make up some numbers and put in for each of these four, and let's see which one produces the highest z-score. Okay, so it says part A, when the mean is much larger than 20. So let's just assume that the mean is 40. And we're just going to say the standard deviation is 10. So let's just say that this would give x equal to 60 because 20 points higher than 40 would be 60 for your x score. And then find the z-score for this data. You'd get 2.00. Okay, part B says when the standard deviation is much larger than 20. Okay, so we'll just assume a normal mean, let's say around 5, and let's say that the standard deviation is 40 because it's much larger than 20, we were told. So this would give a score of x equals 25 because it's 20 points above the mean. And let's find a z-score. So 25 minus 5 divided by 40, about 0.5. How about when the mean is much smaller than 20? So we'll assume that the mean is 5 because it's much smaller than 20. And we'll just assume that the standard deviation is 10, normal standard deviation. This gives a score of x equals 25. Again, we find the z-score to be 2.00. Lastly, when the standard deviation is much smaller than 20. So let's assume, again, that the mean is 5, but this time let's assume that the standard deviation is 2, a really small number. So this would give x equals 25, but it would give a z-score equal to 10. So if we're going to answer the question, it says under what circumstances would the score that is 20 points above the mean be considered a more extreme score? Part D would give us the more extreme z-score.